During part 1 of chapter 8, we saw that you could add a hydrohalic acid to an alkene, and the halogen will add to the more substituted carbon, and the hydrogen to the less substituted carbon, which is a Markovnikov addition. There is a way to reverse the process and actually get the hydrogen to add to the more substituted carbon, which is what we'll look at now. This is going to be a free radical addition of hydrobromic acid. So we can still use a hydrohalic acid, but to have it add in the reverse pathway, we need to add in some type of peroxide. So first we have a ROOR. The R can be any alkyl group, which represents a type of peroxide. The oxygen-oxygen bond is relatively weak, and in the presence of heat, this will homolytically cleave to give us two peroxy radicals. The enthalpy of formation is about 150 kilojoules per mole. So here's our one radical and here's our second radical. We can use one of these radicals in the presence of our hydrobromic acid, and this will break our hydrogen-bromine bond and will ultimately form a bromine radical and an alcohol. Then, once we add in our alkene, you'll notice that this is just a general reaction. The addition will be of the hydrogen, shown here, added to the more substituted side, and the bromine added to the less substituted side. By definition, this is opposite of what we first saw. This will be called Anti-Markovnikov, and just like Markovnikov's rule, it's still in the perspective of hydrogen. So defined here, it says hydrogen adds to more substituted carbon. Alright, so we got an idea of how we formed our bromine radical by adding in a peroxide to hydrobromic acid, which is shown above. Let's look at how the bromine radical will react with the alkene and how and why it adds anti-Markovnikov. So you can see here we have our radical type arrows, which are the half-headed arrows. They're shown to have the radical actually go on the more substituted carbon, and the bromine will go on the less substituted carbon. So looking here, we have bromine with the side that has less hydrogens, and we have our radical on the more substituted carbon. This still follows the trend of radical stability, and we have this methyl group that will donate in electron density. So the reason why it's anti-Markovnikov and not Markovnikov like the carbocation is that the radical mechanism is different than a carbocation mechanism. The very last step will involve the termination of the radical of our product with hydrobromic acid. There's still hydrobromic acid in solution, so this can occur. So we'll add on our hydrogen to the more substituted side, and by definition that's anti-Markovnikov, and we'll also form a bromine radical. This bromine radical will eventually terminate, but for our case, this is as far as we need to go for our mechanism. I'd like to take a moment to look at the enthalpy of the individual steps. So you can see here the very first step is we have our alkoxy radical, and this is reacting with our hydrobromic acid to ultimately form the bromine radical so that we can get our anti-Markovnikov addition. The enthalpy of formation here is negative 63 kilojoules, and all of these are per 1 mole. The second step is going to be the ultimate formation of the radical, which goes on the more substituted side. So let's put in the alkyl groups, or our R groups, and the bromine goes to the less substituted carbon. Here we have negative 12 kilojoules, so this is higher energy. The third step is going to be our termination of this radical, and then the regeneration of more bromine radicals. Here's our R groups to show that the hydrogen went to the more substituted carbon. Our enthalpy of formation here is negative 25 kilojoules. So comparing the three, you can see that the second step is the highest energy, and just like the carbocation formation, This is going to be our rate limiting step, or our slow step. And the second step, other than our formation of our bromine radical, will be our fast step. Okay, I wanted to take a moment to differentiate between the Markovnikov pathway and the Anti-Markovnikov pathway. So the one that we've been looking at in this part of Chapter 8 is adding in a peroxide to hydrobromic acid to give our bromine radical. You'll notice that this will put the hydrogen on the more substituted carbon and the bromine on the less substituted carbon. This will be our Anti-Markovnikov type addition. In the addition reaction that we looked at in part 1 video, we just added hydrobromic acid without the peroxide, and we did not get a bromine radical. This went through the carbocation intermediate. It added the bromine to the more substituted carbon and the hydrogen to the less substituted carbon, which is our Markovnikov pathway. Take time to write out the mechanisms to both and be able to convince yourself why each one undergoes different types of addition. Our next type of addition reaction involves adding water and a catalyst, which will be an acid catalyst, to an alkene to produce an alcohol. The alcohol will add to the more substituted carbon, the hydrogen to the less substituted carbon, which will be a Markovnikov addition. Before we look at the mechanism, let me just take a moment to remind you of just general chemistry acid-base type reactions, where we add a proton-containing acid to water will produce hydronium and a conjugate base. For these mechanisms, we're going to use the hydronium species, which comes from water and the catalytic acid. Once we have the hydronium, let's take a look at how this mechanism will occur. We'll take our pi bond and react it with the acidic proton of hydronium. We're going to add our carbocation to the more substituted carbon and our hydrogen to the less substituted carbon. And once we pull that proton away from water, or from hydronium, we produce water. This water will then be able to act as a nucleophile and attack our carbocation. When this attaches, we're going to get oxygen with 3 bonds in 1 lone pair, which has a formal charge of 1. And in the very last step, the acid catalyst will be regenerated. Notice the hydrogen added to the less substituted carbon and the alcohol to the more substituted carbon. So, not too much different than the addition reaction of a hydrohalic acid. The only thing that's unique is water acting as a nucleophile will give a positive charge once it's attached, and we will regenerate our acid catalyst in the very last step. So this last step is a little bit different than what we've seen before. The first step is slow, and the second 2 steps are quick. Here's an example with propene and acidified water, or water with an acid catalyst, to produce propan-2-ol. You'll notice that the hydrogen will add to the less substituted carbon, and the alcohol will add to the more substituted carbon, which is by definition Markovnikov addition. Take a few moments to work through the mechanism and convince yourself of this pathway. Another type of addition reaction involving an alkene will form a Markovnikov type product with an alcohol is using the Oxymercuration-Demercuration process, which uses this mercuric diacetate structure, HgOAC2, which I'll elaborate on in just a moment, with the addition of water to form an alcohol and a mercuric acetate linkage, which can then be removed with the reducing agent. This reducing agent is known as sodium borohydride, and it'll put a hydrogen there. Some alkenes are sensitive, or if we have an alkene that's part of a more complex molecule that is sensitive to acid, you may want to use this instead of the acid-catalyzed hydration. So I'd like to elaborate on the mercuric diacetate structure. which is HgOAC2. Now before I look at this structure, I want to remind you back to a structure that you may be familiar with, a weak acid, of acetic acid, which is household vinegar. The structure is shown here, CH3, C double bond O, OH. So you remember if this will dissociate to produce our proton, we'll have acetate. So here is our acetate, which they've abbreviated as OAC. We're actually going to use 2 of these acetates connected to our mercury. Now here's the expanded version of our HgOAC2. You can see we have our mercury in the center, and then we have these 2 acetate linkages on the left and right. In the presence of water, this will dissociate into these 2 ions. We're going to get an acetate, and then we're going to get this positively charged mercury complex. It's this positively charged mercury complex to the acetate that we're going to use in our oxymercuration reaction. Once we have our mercury fragment, it can act as an electrophile with the alkene, which will act as a nucleophile, as we've seen with all the addition reactions. This is going to ultimately form a 3-membered ring with mercury. It's called a mercurinium ion. The arrows, you can have an arrow going forward to form the 3-membered ring. You can also have one going forward and coming back. This part isn't that important, just as long as you know that it forms a very highly unstable 3-membered ring. Now, this next step is very quick. We want to alleviate this ring strain. So water is going to come in, go to the more substituted side so that we can get rid of the mercury from that substituted side, and attach to the carbon, which will break this carbon-mercury bond. Also takes care of the positive charge on the mercury. We end up with this structure with now the water attached, which will have a formal charge of 1, and just like with the hydration step, we're going to pull off a proton of the water that's attached to give us the alcohol. We'll generate a little bit of acid in that step, but not enough acid to be able to affect the alkene that may be sensitive, which is the reason why we're doing the Oxymercuration-Demercuration reaction. The last step is going to remove the mercury fragment and produce a hydrogen using sodium borohydride. This step, just know the reagent and that it removes the mercury acetate fragment. The mechanism you'll actually worry about in second semester chemistry. Again, this process is also Markovnikov, in that the hydrogen will add to the less substituted side and the alcohol to the more substituted side. This will wrap up part 2, and I'll have another video for part 3 shortly. Thank you.